Hi, I'm Dongbin Kim from University of Nevada, Las Vegas. I would like to thank for American Control Conference 2020 Denver Committee for giving me this opportunity. I'm very excited to present my work in testing and evaluation platform for haptic-based aerial manipulation with drones. First of all, let me show you examples of aerial manipulator. This aerial manipulator shows hose insertion task. The next video shows using dual arm manipulator to perform valve turning task. And this video shows the aerial manipulator with parallel mechanism to do visual servoing. And this aerial manipulator attached a gripper on a parallel mechanism manipulator to perform a pick and place. Our lab is in a project called INSPIRE, Inspecting and Preserving Infrastructure Through Robot Exploration, under U.S. Department of Transportation. Our lab is called to design a mobile manipulating unmanned aerial vehicle called MM-WAV to provide innovative tools and methods for the expert workers for bridge inspection, maintenance, sensor installation. And there has been several designs for MM-WAV to a task in the hose insertion, visual servoing, pick and place, contact inspections. There has a future vision as we're going to fly this autonomously. It's been almost 10 years, but still, we didn't see a full implementation yet. So we decided to look what's actually going on in bridge inspection and maintenance. In bridge inspection and maintenance, the bridge worker perform tasks like drilling and riveting, and depending on the bridge condition, they gather several experience. They have to check their sense of touch, or they have to hear during the task, and they also have to check the weather, whether it's snowy or rainy. This experience will gather as a data set. As this data set accumulated for many years, this bridge worker became an expertise. And I want to look at how long it took for the bridge worker to become an expert, and then I'll look it up at the Missouri Department of Transportation criteria that they require 7 years of experience in bridge maintenance and inspection. And our lab's original mission is to make this MM-WAV do tasks like this. So learning from here, and also there's been no full implementation of MM-WAV, we thought that maybe the mission is too broad, and there are so many things to consider for us to design MM-WAV in bridge inspection and maintenance. So we got this idea of Human-in-the-loop MM-WAV, which is that we provide expert workers who are skilled, experienced, knowledgeable, a MM-WAV, and this MM-WAV provide haptic feedback. So with this, the expert workers assess the object properties, and then they supervise the task, and then they perform teleoperated manipulation with MM-WAV for bridge inspection and maintenance. So we call it Human-in-the-loop haptic-based MM-WAV. In this paper, we design and build test and evaluation platform for haptic-based aerial manipulation. We designed this to provide safe and repeatable pre-flight test environment for haptic-based aerial manipulation. The design is motivated from our old work in System Integrated Sensor Task Rig, SISTER. It is designed to emulate drone motion in XYZ, and you can see the video that a dual arm on the task rig perform object pick and place. If you can see this, that we attach the arm on the rig, and then when it moves around, you can visually see what's going to happen in actual flight test. So we thought that this will provide safe and repeatable pre-flight test environment, and we use this design for motivation. First of all, we designed the manipulator. we had to choose between serial mechanism and parallel mechanism. We chose parallel mechanism because it has lower impact on center of gravity and higher precision in manipulations. This design is actually addressed in our previous work, and it has all details of 6-degree of freedom parallel mechanism. And this slide shows the construction. So we used 3D printed plates and joints, and the boom is built by carbon fiber, and we use 8 servo motors controlled by Porolo servo controller, and inverse kinematic server is embedded. So this video shows the manipulator follow the trajectory in the video, and then the weight is around 400 grams. Then we designed this haptic system. We chose elastic force for haptic feedback, which can be easily explained by Hooke's law. We chose this elastic force because Haptic 101 teaches elastic force for the first example. And we chose 3DS system haptic touch as the device because it is broadly used in robot surgeries. In this device, force is exerted on the joystick while rendering the force, and it has an exertable force maximum in 3.3 Newton. It can render force like elastic, friction, impulse force, and we customize this device by OpenHaptics SDK. To integrate this haptic system to the manipulator, we fabricate end effector 3D printed, and we attach strain gauge for force sensing. Also, we attach paper clip for spring pull-up. And also, there is a customized module that reads sense force. We perform sensor calibration with weight. During this calibration, we tried several thickness for end effector because we want to find minimum forcing or sensing range close to 0. And considering the formula at the left side bottom, we found the thickness as 1 millimeter. Therefore, we got this force sensing range from 0.1 Newton to 6.29 Newton. But actually, haptic device render the force in XYZ, 3-dimensional. But what we sense here is color by the manipulator. So I use this joystick position vector formula to make the force broken into 3-dimensional vector so the operator feel the precise forces. Finally, we build a proof of concept MM-WAV, and it has a Q450 quadcopter frame, and it has a payload 2.4 kilogram. We use this Pixel 4 autopilot, and we use this 11.1 2200 milliamp LiPo battery. And then we attach this leg for the workspace, and you can see this manipulator attached under the quadcopter. Finally, we build a test and evaluation platform. And this platform has a gantry-based system, and it emulates drone motion in XYZ, and the size is 40 cubic foot, 5 by 4 by 2. And then you can see the MM-WAV is attached on this, the gantry-based system end effector. And then we attach the zinc spring from Lowe's under the MM-WAV, and then we use robot operating systems. And the operator used the haptic device joystick to control the manipulator to spring pull up in Z-axis. And then the picture on the left shows a zoom in photo of how it gets pulled. So when the elastic force is sensed, it's rendered to the operator, so operator can sense what kind of force is exerted. Then we perform haptic manipulation tasks in this platform, and the plus on the left shows the blue as a sense force, and the red dot shows what's actually rendered to the operator. We actually cut the sense force to the half due to the haptic device force rendering limit. And the green plot shows the joystick input. And we capture the forces every 10 millimeter displacement, and the table on the right shows the result. So sensor force is from 0.71, 1.44, 2.22 Newton, respective to 10 mm, 20 mm, 30 mm displacement, and you can see the render force is around half. From this result, we calculate the spring constant is 0.073 Newton millimeter. With this result in mind, we compare our result to the one from flight trial. We conducted MM-WAV flight for validate and verify the result from test and evaluation platform because we want to design test and evaluation platform to provide safe and repeatable pre-flight test environment. And then we design a cascade proportional derivative compensator for MM-WAV stabilizations. And then you can see there is a spring and MM-WAV in the motion capture arena. And then we use a motion capture to capture the positions of the spring tip, MM-WAV, and MM-WAV end effector. And during the test, operator used the haptic device to control the manipulator when MM-WAV approaches to the spring to pull up the spring. This slide shows details of cascade PD compensator. Inner loop shows the controller of PICSOC which provide an internal estimator. But inner loop control wasn't enough for the precise MM-WAV aerial manipulation. So on top of that, we designed an extra loop controller, which is called outer loop. We define disturbance is from UAV motion and also inner loop controller drift by the sensor. And the error is computed by reference position and the MM-WAV position by motion capture. Then from the PD compensator, the compensator convert the error into control signal. Then control signal will be converted into the reference speed for the PICSOC controller. So this video shows flight trials. In the trial, the operator controlled the MM-WAV to pull up the spring. And after spring pull up, manipulator try to disattach the manipulator on the spring and landing. And this slide shows the test flight result. Figure on the left shows the MM-WAV position error and the distance between MM-WAV to spring and the force measurement. Total flight time was 80 seconds and the force is sensed between 63 to 60 seconds. But there was a flight fluctuation which caused the incorrect measurement. But considering the MM-WAV and spring distance plus manipulator joystick input, we could find the displacement area. So in the figure, the yellow area shows when the displacement 10 mm, red for the 20 mm, and gray for 30 mm. And it shows that the similar pattern to the result from test and evaluation platform, which is a gantry-based system, and we got this error around 10%. And then we think this proved the test and evaluation platform's efficacy. And also, we conclude that this pre-flight testing environment from test and evaluation platform provides a safe and repeatable manner before the actual flight. So this work contributed in 6 degrees of freedom parallel manipulator design for MM-WAV and a choice of haptic device for elastic force feedback. And we calibrate the end effector sensor, and then force sensing range is calculated by the end effector thickness. Finally, test and evaluation platform is built for haptic-based aerial manipulation, and the result from a T&E platform is validated and verified from the flight trial. And then we conclude that the flight trial shows the similarity to the results from the test and evaluation platform, and this shows the T&E platform's efficacy. In the future, we're going to case study tasks in the bridge inspection and maintenance and power line and windmill. For doing that, we're going to test with different haptic feedback type like impulse and friction forces. Thank you very much.